In part D, we have a number of things going on, so we need to read this very carefully. We have the Taylor series for G about x equals 0, when it's evaluated at x equals 1, is an alternating series with individual terms that decrease in absolute value to 0. Now I've highlighted those there or underlined them because those are the key words to show that this series for G is or passes the alternating series test. So let's talk about the alternating series test for just a second. And if a series passes this test, it means that the series converges. The first criteria is that the series must be strictly alternating. Second, terms decrease in value. And third, limit as n approaches infinity of a sub n is 0, which means that it passes the nth term test. Passes the nth term test because the limit as n approaches infinity of a sub n is 0. Now if that's true, then the series converges. Now oftentimes these last two criteria, terms decrease in value and the limit as n approaches infinity of a sub n equals 0, are written like so: decreases to 0, or decreases in absolute value to 0. And that's the way that it's stated above in this particular problem. So we know that this series definitely converges here. And so first of all, we want to use this information. We're going to use this information in the latter part of the problem. First of all, we want to use the third degree Taylor polynomial for G about x equals 0 to estimate the value of G of 1. So you recall we have here t sub 5, which is the fifth degree, but t sub 3 would just be the series where the highest exponent is third power. And we want to use that to estimate the value of G of 1. So G of 1 is roughly equal to t sub 3 of 1. We're just going to plug in 1 for x's there. We get 1 minus 1 over 2 factorial, which is just 2, plus 1 to the third, which is 1, over 3 times 4 factorial. And we can leave this in factorial notation. That's no problem. Right, so that is our estimate of G of 1. Now, anytime we truncate a series, in this case to 3 terms, there will always be some error associated with it. And there is an alternating series remainder theorem. And it says this: the error caused by using only n terms will be less than the n plus first term and have the same sign. As the n plus first term. So remainders are easy to calculate, or error bounds are easy to calculate with alternating series. Now we want to show that G of 1, which is the actual, minus t sub 3 of 1, we know that that difference, and we'll talk in terms of absolute value here, that difference has to be less than the first excluded term. And let's talk about the first excluded term here. Since we were only using the third degree, the first excluded term would be x to the fifth over 5 times 6 factorial, and so the error bound has to be less than that. Of course, we're plugging in 1 for x, so it has to be less than 1 over 5 times 6 factorial, which itself is going to be less than 1 over 6 factorial, which is given there. So we've shown by the alternating series remainder theorem that the difference between the actual, we'll call this actual, and the estimate has to be less than the first excluded term, which would be 1 over 5 times 6 factorial, which is less than 1 over 6 factorial. And that settles or explains why the estimate has to differ by less than that. And that'll do it for this problem.